And now, may the force be with you. Radiative forcings, that is. I know that that's a corny joke, but taking everything we've talked about so far in this class, all the human causes, all the natural causes, and putting it all together to take a look at one main thing. Are humans the cause of climate change? Spoiler alert, yes. That being said, how do we know that for sure? We know that by looking at what are called radiative forcings. Let me explain what a radiative forcing is. So a radiative forcing is a value that we assign to each thing that we have done here to the Earth system to our climate. So basically what we do is we assign a number, a value for quantitatively, numerically determining a forcing's effect on climate. The bigger the number, the bigger the impact. So the bigger the number, the bigger the impact. Positive numbers indicate warming, meaning that when you see a positive number, that means that heat has been added to the Earth system. Wherever you see a negative number, that is a cooling effect. A cooling effect. So in this case, positive does not mean good, it means warming. And in this case, negative does not mean bad, it means cooling. All right, so that being said, let's talk about these individual forcing factors. So some forcing factors have a warming effect on climate. Good examples, increases in greenhouse gas concentration. Because we have more greenhouse gases, carbon dioxide and methane specifically, those things allow heat from the sun to continue in, but they trap heat trying to escape. As a result, more heat is now present near the surface of the Earth. That leads to warming. That is a positive forcing. Another positive forcing could be an increase in sunspot activity. More sunspots mean more sunlight. More sunlight means more warming, more heat. That is another positive forcing factor. Others have cooling effects on climate. So for example, an increase in aerosols. As we mentioned earlier, aerosols are believed to have a net cooling effect. So more aerosols, what that actually means is less sunlight reaching the surface of the Earth. Therefore, there's less heat in the Earth system. That is a cooling effect. That would be a negative forcing factor. So these warming factors, these are positive. These cooling effects, these are negative. These are negative. So that being said, what actually is a radiative forcing? Well, radiative forcing is a change that has happened to Earth's energy budget. A change to Earth's energy budget. So we've talked before that there is a certain amount of heat that comes in and a certain amount of heat that goes out. Radiative forcings are changes to that budget. Just like, let's say you have a budget and let's say you decide to eat out less. That reduces your spending. That affects your budget. That is basically what a radiative forcing is. It is a change to Earth's energy budget. Now, that being said, what do we compare this change to? Well, so first off, these changes are given in a set unit, a unit called watts per meter squared. And the reason why we use that unit is that is the unit that we use for incoming sunlight. Whenever we talk about energy here on the surface of the Earth, we're talking about it in watts per meter squared. Basically, that is the amount of energy that a square meter of something either receives or gives off. Now, that being said, here at the surface, or here at the top of Earth's atmosphere, the top of Earth's atmosphere receives approximately 341 watts per meter squared of sunlight, meaning that the surface of the Earth receives, or sorry, not the surface, the top of Earth's atmosphere, 341 watts per meter squared of sunlight come in. Of those, 102 are reflected out. And then the Earth emits 239. So radiative forcings are things that change this. Things that change this. So this right here, this is just basically the same previous diagram. There's a lot of different components on this. I'm not going to walk through each one of these components ad nauseum. What I do want you to know is that Earth's energy budget is balanced. On average, Earth receives about 341 watts per meter squared of radiation. It reflects out 102 watts per meter squared. That leaves us with a total of 239 that are absorbed by Earth's atmosphere and Earth's surface. So the grand total is we get 239 that come in. And then Earth emits a certain amount of long wave radiation. Some of that long wave radiation is absorbed by clouds, radiated back down to the surface of the Earth. Some of it escapes. Some of it goes through other processes such as latent heat exchanges, sensible heat exchanges. When we add all of that up, the amount of radiation that leaves the Earth system is 239. So 239 in, 239 out. That is Earth's energy budget. Well, radiative forcings are things that change this budget, that either change what comes in. So maybe the sun gets a little bit brighter and instead of 341, we get 342. We get 342 in that case. Or let's say albedo changes. That reduces the amount of radiation that's reflected. That also changes our overall income. On the other hand, if we change our land surface changes our land's ability to evaporate water. If we get rid of vegetation and we replace it with concrete, we've reduced our evapotranspiration. That causes that number to change. So I know that you're probably pulling your hair out and you're getting bald like me. All I want you to know right now is that a radiative forcing is something that changes Earth's energy budget. That's all I want you to know right now. A positive forcing is something that net adds heat to Earth's system, heating Earth up. A negative forcing is something that removes heat from Earth's system, cooling it down. Now, that being said, each one of these is actually compared to the year 1750. So basically what climate modelers have done is they have reconstructed Earth's energy budget for the year 1750. So this was before the greenhouse effect had a big enough effect. This is before humans had really any major impact on Earth's system. Now, it's not to say we had zero, but we had very, very little compared to today. And then we compare that to the 2011 energy budget. And the radiative forcings are basically what has changed between 1750 and 2011. Now, why 2011? Well, 2011 was the most recent data from the previous IPCC report. The next IPCC report will be out in the next few years, and we'll probably see updated numbers. But this is for our most recent IPCC report, which was released in 2014, meaning that they had to have a few years of number crunching and analysis. So radiative forcing is simply a change to Earth's energy budget caused by these individual components. So what are these individual components? Well, we've actually talked quite a bit about them already. Increasing greenhouse gases. Increased greenhouse gases result in more heat being trapped near the surface of the Earth, That now means that there's more heat in the Earth system. That is a positive radiative forcing. So this is a positive radiative forcing, things such as increased carbon dioxide, increased methane. These are positive forcings. Once again, that doesn't mean good. That means warming. These have caused more heat to stay in the Earth system. These have caused more heat to stay in the Earth system. Ozone. We've mentioned ozone briefly. Ozone levels have been depleting over the past roughly century. However, they are recovering. Ozone does have a little bit of a greenhouse effect near the surface of the Earth in producing smog. The presence of ozone is also a positive forcing mechanism. This is also a positive forcing mechanism. Now, things that have depleted ozone can actually have a negative forcing mechanism, but ozone overall is a positive forcing mechanism. Land use changes, these include things such as deforestation, urbanization. Believe it or not, the net human impact has actually been an increase in albedo. Here's why. And I actually experienced this past week. I actually drove through the mountains. And if you drive through mountains in the wintertime when it's not snowing, maybe a few days after a snowstorm has occurred, what you'll notice is the trees are largely free of snow. And so they're dark. Well, dark things have a low albedo. They absorb a lot of sunlight. Meanwhile, the ground beneath them is white. It's very light colored. There's a lot of reflection. There's a high albedo near the ground. Well, in a densely covered forest, the ground is shaded. So no sunlight hits the ground, no sunlight reflects off the ground. Instead, all of the sunlight is absorbed by the trees, heating the earth up. However, if you chop down those trees, what you now have left behind is snow-covered ground. That actually results in higher albedo. So pre-industrial times, before we were doing any kind of deforestation, there was actually lower albedo because all of the snow that was on the ground was being covered by trees. Then we came along, we chopped down those trees, that resulted in a higher albedo. Now, that being said, there actually is a large uncertainty here, and I'll talk about uncertainty in a moment. Okay, so those are just a few examples of different forcings. Now let's put it all together, and I know that looking at this image, you kind of feel like a deer in the headlights. Let me explain what's going on here. So if you notice, there are approximately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 categories. These three are kind of lumped up into category 2. All right, let me tell you what's happening here. Each one of these things is an individual radiative forcing. Each one of these things is an individual radiative forcing. So for example, let's look at number 1 really quickly, carbon dioxide. Carbon dioxide up here has had an impact on Earth's energy budget, has had a radiative forcing on Earth's energy budget. The intensity of the forcing, the intensity of the forcing is determined by how wide the bar is. In this case, the width of our bar goes from our 0 line all the way out to approximately, if I were to dash my way down here, approximately 1.6 watts per meter squared. What that means is that from all of the analysis we've done, it is believed that since 1750, carbon dioxide has been responsible for an additional 1.6 watts per meter squared of additional heat being added to the Earth to the Earth system. Now, that being said, we can't be 100% true or 100% confident that 1.6 watts per meter squared is the set number. No, anything that you do has some level of uncertainty. Maybe it had a little bit more, maybe it had a little bit less. That's where this bracket right here comes in. This is what's referred to as the uncertainty. And for those of you who are statistics nerds out there, uncertainty is basically given at a 95% confidence level. Here's what this means. So the calculated number that we came up with was 1.6 watts per meter squared. However, we can say with a 95% statistical certainty that carbon dioxide has resulted somewhere between 1.4 and approximately 2.1 watts per meter squared of warming. So that's basically what that suggests. That suggests that carbon dioxide has had somewhere between 1.4, actually more like 2.0. Get my numbers right here. Between 1.4 and 2.0 watts per meter squared of warming. That is carbon dioxide's uncertainty, somewhere between 1.4 and 2.0 watts per meter squared. So we can say with 95% statistical confidence, that is considered the gold standard, that carbon dioxide has resulted in anywhere between 1.4 and 2.0 watts per meter squared of additional warming. All right, so that's what's going on there. For methane, so that's the second line right here. We see it has just a little south, just a little short of 1 watt per meter squared of warming, but it could be anywhere between 0.75 and roughly 1.25 watts per meter squared of warming. And so each one of these different line items, whether it's methane, halogenated gases, nitrous oxide, short-lived gases, aerosols, changes in clouds, every one of these has a determined value. Every one of these has a determined value. Now, that being said, if you notice, most of the bars lie on one side or the other of the 0 line. These bars that are entirely orange, such as this one, this one, this one, this one, this one, and this one down here, those all lie on the positive side. Those are all positive forcings, meaning each one of those individual forcings has caused warming. Now, if you notice, a few of these bars lie entirely on the other side, the negative side, specifically line items 7 and 8, changes in clouds due to aerosols, changes in albedo due to land use. If you notice, both of those are big blue bars entirely on the left-hand side of the 0 line. These are negative forcings. These are negative forcings, meaning that these have actually had a cooling effect. Okay, Terrence, what about this one this one, and this one. So the halogenated gases, then line item number 5, one of the short-lived gases, and then aerosols altogether. If you notice, all 3 of these, their bar actually lies a little bit on the positive side and a little bit on the negative side. These are what are called statistically insignificant. These are what are called statistically insignificant. Or actually, the better term, not statistically I don't think I spelled that right. That's why I majored in math. Not S-T-A-T, not statistically significant. Here's what that means. When a forcing factor is not statistically significant, we cannot say with confidence that it causes either warming or cooling. We cannot assign it a positive or a negative. We simply don't know. There's not enough evidence to suggest either one. It could either be warming or it could be cooling. We don't know with statistical confidence which one it is. So that's what not statistically significant means. That means that it could actually have either effect. We don't know. Its uncertainty is too big. And if you notice specifically for the aerosols line item, that uncertainty bar actually lies on both sides of the 0 line. What that means is that that impact can be anywhere between positive and negative. We just don't know. So we don't really know. We cannot say for certain what those impacts are. Now, once we add all of this up, specifically line items 1 through 8, what we get down here, the net total due to human activity. Well, the net total due to human activity has a value of approximately 2.3 and an uncertainty anywhere between 1.3, roughly between actually 1.2 and 3.7 or 3.8. Basically, what this means is the net total due to human activities has been warming. When you add all of these individual line items up, the net total due to human activity is warming. Here's the other thing that's really important. There's only one real natural thing that could have any real impact, and that has to do with changes in energy from the sun. There has been a slight increase in solar activity since 1750. In 1750, we were coming out of the Maunder minimum, and so solar output has slightly increased. That's the only natural thing that could even register on this whole scale, and that's right here. It's a positive forcing, but it's really, really tiny. Compared to human activities, it's almost negligible, almost nothing. So when you compare natural changes, natural forcings, to forcings caused by human activities, the answer is simple. It's us. It's us. We are at fault. We are the cause. We are the cause. So for this week's module activity, I'm actually going to have you investigate this a little bit more. For this module, please let me know if you have any questions, comments, concerns, and I will see you all next time.